Geometric isomers form in alkanes. Now, geometric isomerism is a type of what's called stereoisomerism, which means we need to consider these structures in 3 dimensions, not just in 2 dimensions. And geometric isomers involve atoms or groups of atoms in different sequences around a double bond. Now, if you look at these diagrams, the top one shows a butene molecule, so we've got 4 carbons here, and we've got the double bond in the middle, and you see how the carbon structure, the parent chain, crosses that double bond. Whereas in the second structure, the carbon chain, the parent chain, stays on the same side as the double bond. Now, when you've got the molecule crossing the double bond like that, we call that trans as in across. And here, where the molecule stays on the same side, or the groups stay on the same side of the double bond, we call that a cis isomer, so cis for same. So if we name these properly, the top one is called trans-but-2ing, because the double bond's between the second and third carbon, and the one on the bottom is cis-but-2ing. Now, why are those different structures? Why aren't they just the same structure? Well, if you consider that in alkanes you have single bonds, those single bonds can rotate around. Now, if you have a go with the molymod kits making an alkane and an alkene, you'll see that that single bond allows the molecule to rotate around it, whereas this double bond in the alkene causes a rigidity in the structure, and where those 2 carbon atoms are bonded by two bonds, by a double bond, it doesn't rotate. Okay, so carbon atoms that link by single bonds rotate around the axis of the bond, whereas in alkenes the double bond is rigid. It doesn't allow that rotation around the double bond, and that's what allows these geometric isomers to form. So in this diagram you can see that the halogen or green atoms are on the same side of the double bond, so that is a cis isomer, and here we've got the same structure, the halogens, sequentially different, or in stereo, in 3D they're different, and this crosses the double bond, so that is our trans isomer. Okay, so let's have a look at these. Which of these structures would actually show us or give us geometrical isomerism, or cis and trans isomers? This one here?
Carpi.
Excellent, that's right, this one will, because you've got a double bond and each carbon has 2 different groups attached to it. If you were to remove one of those carbon atoms, flip it over and then rejoin it, then you would have the trans isomer. What about this one here? No, not that one, because this carbon on the left has 2 groups the same. If you were able to remove that and then put it back upside down, it would still look exactly the same. So no cis or trans isomers. What about this one here? Bottom left. Again, carbon atoms with identical groups on them. How about this last one?
Carpi.
That's right, here each carbon around the double bond has 2 different groups off it. So if we were able to remove one and flip it over, we would have the trans isomer, this being the cis isomer.